Okay, everybody, we're going to get started here. So this evening, we're going to be exploring some ideas in the middle and towards the end of chapter 9. We've got some really great stuff to talk about in here. I think these are really fascinating, far-reaching ideas for us. I enjoy all the ideas this semester, but I can only get so excited about stoichiometry and combustion analysis. The stuff we're talking about this evening, I think is really interesting. So I'm glad we can share some time and discuss it. So as we get started here, as you might recall from conversations or information I've shared along the way, I've got two pets that usually join us. Okay, I got my cat Rosie, who you've seen, but I don't think I've shared any pictures of my dog Rufus. So I want to share and show you a couple pictures of Rufus. So as I share these, you'll also get some glimpses of my house because these are all in my house. So here was Rufus before dinner. This is the room where I'm almost always broadcasting here. So that's my pile on the floor. You can see he's ready to pounce, okay? Hanging out. Wintertime Rufus, looking a little dapper there with his little, I don't know, ascot or something. Hard at work Rufus, and in bed Rufus. So that's Rufus for you, okay? He might join us this evening, we'll see. Looking ahead here, I'm trying to make a plan as we move towards our third exam. So if you look on the syllabus, one thing that jumps out is it's going to be on Wednesday instead of Monday. So it's on April 7th on a Wednesday. So I just want to make sure we get that in on our calendar so that we're not looking to take the exam on a Monday. So it's going to be on a Wednesday instead. Now, about 1/3 of our class, you all have labs on Wednesday night. So I saw that a message was sent out. It was yesterday through Carmen, telling everybody the plan for what goes down if you happen to have a Wednesday night lab. So I'm just curious within this. Let me shoot you a polling question. 1, 2, 3, or 4. What category are you in here? Does it not apply to you? You saw it, you know the plan. For some reason you didn't heed it, or you're confused by it. Just want to make sure we're all on the same page here. We all have the same plan. Okay, so as those are coming in, seems like we're mixed between, there's just a few folks that saw it and were confused by it. Other people, you either it doesn't apply to you, you have the plan, or you haven't quite looked at the details yet. I'll find answers. Let me take a second. Let me share with you what the plan is. So the plan is if you have a Wednesday night lab, you're going to have a 12-hour window of time in which you can start and take the exam. And that's on the Thursday, the very next day, okay? April 8th, from 8 in the morning till 8 at night. Anytime within that 12-hour window, you can work the exam. Now, when I say work the exam, you have exactly the same time limit you always would. You do not have 12 hours to complete the exam, but you can start it anytime and work it through within that time slot. So if I were you, if I was a Wednesday night lab person, I'd be putting on my calendar sometime, make a plan for when you think you're going to be taking it on that Thursday. You don't have to do anything to make this happen. You don't have to make any other kind of special request, nothing else within the system, okay? This applies for the folks that have a Wednesday lab. If you have a Wednesday recitation for this class, you're going to be taking the exam instead, okay? This idea of taking it's not really an alternate, taking the exam on Thursday instead of Wednesday night, that's for folks that have a conflict in terms of their lab itself. Check the message, okay? Check the message. I'm just parroting back what those details were. And let's make sure we get straight so we're good to go for when that exam comes around. Now, I looked as far as where we're at heading into that particular exam. So here we are on Thursday the 25th. As I look, we're going to have the exam then, which is on chapter 7, 8, and 9. For most everybody, it's on Wednesday the 7th, or exam, if you have those Wednesday labs, sometimes that next Thursday. So if I was looking at this and trying to break out what our strategy is going to be, tonight we're going to be finishing up our discussion of valence bond theory and starting something called molecular orbital theory, or MO theory. I think we can get almost all of that MO theory then taken care of in our next class on Tuesday. There's no class on Thursday of next week. And I think if we can balance it off there, that would make the Tuesday class that we have a review on the same week of the test. So I think as I look at where we're at and where we're going, I think this is a really good distribution. Someone, Margaret mentioned to me that I have a perusal assignment due, I think on the 1st. I'll be able to adjust that. I don't want anything due for you on that particular Thursday. And I'll also be looking to see with like what we have within mastering. Right now we have an assignment on mastering on Tuesday. I just want to make sure that we can balance things off across those. But I think we're in really good shape as the ideas come together. I also looked, and they have 3 really high quality practice exams that are posted in Carmen leading up to midterm 3. I think those would be really effective after we finish up stuff within our class next Tuesday. So as I look with the time that we have and what's in front of us, I think we're in really good shape to try to bring together the ideas. I've been sharing ideas with you all already for chapters 7 and 8, different worksheets or things, suggested problems. Let's see if we can continue and wrap up our ideas here within chapter 9 in the next 2 classes. And then I think we're in really good shape to begin to consolidate some of our understanding, review, and head into the exam. Now, let me ask you this question. Lately, we've had about 50% attendance in our lecture. That's usually how it winnows down as we are at this point. And so I mean, if I was in a regular class, I'd have people look around and see who's there and who's not there. But I want you to speculate for me, okay? You've decided to come here this evening, and about half your classmates haven't. So I want you to think for a second. Why do you think you're here and they're not? I just want your opinion on this, okay? I tried to put together a couple categories, and I'm going to shoot you a poll. It might be about your learning. Maybe you think being here helps you learn more than your classmates. Maybe you feel an obligation. You know, maybe you feel like, hey, I paid to go to class, I'm going to go to class. Maybe you find it somehow more fun, interesting, engaging, or maybe you think it's easier for you to attend than them. Maybe they have other barriers, they're working, there's other technology issues, who knows what. So I'm curious on this. Let me send you a poll. This is all that apply. Why do you think you're here tonight and they're not? Take about 10 more seconds. So here's what folks are saying. I have no right answer, obviously, on this one. I'm just curious. I do want to make it, though, for the time that you have here, let's really maximize your learning, okay? Let's do our very best so that, especially if you're in category 1, if you think that this time helps you learn more than your classmates, let's do our best to make that happen, okay? So our plan right here, we're going to talk about valence bond theory and molecular orbital theory. Both of these ideas, if I think about chemistry 1210, and if you take further chemistry courses at OSU, if you take organic chemistry, for example, in the first semester here in 1210, the most important ideas that you're going to need for organic chemistry are going to be these bonding models. Being able to understand valence bond theory and molecular orbital theory. They will return to those ideas, you know, they'll build on them, but I think in this entire first semester, the ideas that you're going to take into organic chemistry, if you go onto there, are going to be these descriptions of bonding for valence bond theory and molecular orbital theory. Now, within valence bond theory, I introduced it a little bit last time, and people were doing a really good job of asking questions and helping each other within the perusal assignment. So I think now by returning to this, for many of you, this is the third time you've thought about it, maybe the fourth. So I think the ideas are going to come together and you're going to end up with an even better understanding. So what I'd like to do right now to recap valence bond theory, I'm going to spend a little bit of time talking about the concept, what the idea is. I want to help give you a plan for you to follow to work through problems involving valence bond theory. We'll apply that for a few examples, and I want to make clear how the idea appears on tests. The reason I say that is, if you think back to chapter 6, where we looked at the Schrodinger equation briefly, I mean, you could do a whole graduate career on the Schrodinger equation, but in this class, we reduced it down to just a couple of ideas or skills. Same thing here, valence bond theory. It's a really high level topic. I want to try to show you how it's going to appear on the test and what we use it for, okay? So let me talk about the concept first. So the idea here is that to form a covalent bond, we need to have the electron density. The electrons have to be found between the nuclei, between the protons, so they can serve as the glue that holds together those atoms. Now, we know that electrons, they are found in atomic orbitals. So therefore, to form a bond, the orbitals must be allowed to place the electrons between the two nuclei. They have to be aligned properly. If they're pointed in another direction, they're not putting the electron density between the two nuclei. Now, when I think of atomic orbitals, I might think about it a little differently than you do. I'm thinking about atomic orbitals as a description of standing waves. Now, why do I say waves? If you think back within chapter 6, a feature of our what was called our wave particle duality, something like an electron also has characteristics of a wave, which I think is a cool idea. We talked about the de Broglie wavelength, about how something like an electron has a measurable wavelength. And in fact, electrons, they exhibit behavior of waves. They'll be diffracted, for example. When I look at this radio probability distribution function, I'm seeing nodes. I'm seeing spots where it goes down to 0. That to me is a description of what a standing wave would have. For an atom, these atomic orbitals, they were constructed to describe the probability of finding the electron somewhere around that particular nucleus. And I'm thinking about that probability of where it would be found as having characteristics of a wave. And when I mention a standing wave, let's say we've got this child here in the tub, okay? The child here is in the tub, and let's say the child is wiggling at a particular frequency. What you would find is you'd find that the water around the child would be disturbed. And if the child is going and wiggling at a particular frequency, you could set up a standing wave. You would have a pattern there for the waves in the water. Now, what happens when another atom approaches? It can change the way that these atomic orbitals are configured. Instead of the electrons being only attracted to one nucleus, they're now being influenced by the other atom. They're being attracted also to that other nuclei. This is going to change the way that the standing waves are set up. We're changing the conditions of that are leading to these standing waves. So instead of having just one kid in the tub, let's say we put 2 kids in the tub. Now we've changed the condition. The waves that we have being set up in here, they won't be exactly the same because they're now responding to both of the kids in the tub. If you're hanging with me on my analogy, if you think I'm just looking for an excuse to use this photo, I probably am, okay? But what we're doing is we've changed the conditions for how the waves exist. We have new standing waves. This is what's taking place when we have our hybrid orbitals. We had an initial set of atomic orbitals around the atom all by itself. Now when a neighboring one comes in, we change the conditions around there. We're not breaking any rules. We're just looking at the new standing waves that form, the new atomic orbitals that form. That's my concept for what's going on. I wish we could have an essay question on the test. I love that if it's like, if all instructors got to like add one question. And I had mine be a figure with these two kids that came up, and everyone else would be like, what the hell is going on Tuesday, Thursday night, in that class? That's what I'd want our discussion to be on. But we're not going to have our discussion on that. But that's the concept here. So the concept is we're going to be making new standing waves that are these hybrid orbitals. So what's the plan that I want you to do? I think we need to know when we're going to use hybrid orbitals and how to use them. So first of all, when will hybrid orbitals be used? So when do we need to use this to explain bonding within our valence bond theory? You will never need hybrid orbitals for an exterior atom. They are already going to have atomic orbitals that are correctly aligned with the neighbor. You will never have to hybridize something that's on the outside of a molecule. In these diatomics, HH, H2, CO2, HCl, all of these, we already had an orientation that would work. And I will say, you will always need hybrid orbitals for a central atom. When we are looking at something like N2, that was another case where we did not need to hybridize them. We could still bring them together because we had even 3 different ones that were aligned properly that could lead us to have the triple bond. So here I'm showing different types of bonds. Let's practice an idea from last time. So I show 6 different sets of bonds being formed here. How many of these would you describe as pi bonds? Let me send you a poll on that. How many of these do you think that are going to lead to pi bonds? I'm not asking which ones, but how many? Take about 10 more seconds. So we're split on this. We've got folks, the main number that's being directed here, selected here is 2. And then also a mix between not really understanding the question or really don't know how to go about it. I agree with the answer that there are 2. I think both of these are going to be leading to pi bonds. Let's go back and think about, and we're going to need this later on. What is our definition for what makes something sigma or pi? Sigma is when we have electron density along the internuclear axis. So along the line between the 2 atoms. It could be formed from a pi orbital, a p orbital with another p orbital, a 1s with a 1s, a 1s with a 3p. All of these are putting electron density along the internuclear axis. These are all designated sigma. The ones that are putting electron density when they overlap off the internuclear axis, maybe it's above and below or front to back, those are what are going to have this pi designation. So the pi designation, the sigma designation, it depends on the symmetry, the resulting shape that we end up with. And it appears in something like N2, we can get sigma and pi bonds just from the original atomic orbitals. How about this one? Now, based on when I just said, as far as when we will or will not need to have hybrid orbitals, I circled different ones on here. Take a second, look at this one. Which of these do you think are going to require hybrid orbitals to explain their bonding? Which of the atoms within here, look at it closely for me, which of the atoms that are circled are going to require hybrid orbitals to explain their bonding? So given what our description was just a moment ago, we will not need to hybridize any of the ones on the outside, on the exterior, but we are going to need to hybridize all of the central ones. And by central, I mean, it's not one of the ones that's stuck on from the outside. F stuck on from the outside, this hydrogen stuck on the outside, even this oxygen stuck on from the outside. The only time that we're going to need to hybridize them, and when I say need to be able to have that as a feature to explain the bonding using valence bond theory, are the ones that are on the inside of the molecules. These would be the ones where we need to hybridize them. So then the next question, so we've already, first of all, the first part of the skill is based on the Lewis structure, do we need to hybridize it? Second thing is, okay, if we do need to hybridize it, how do we choose which kind of hybridization to use? The electron domain geometry for that atom, it will tell us the kind of hybridization we need. If the environment at that atom is linear, we will use sp hybridized orbitals. If it's trigonoplanar, we use sp2. And if it's tetrahedral, we use sp3. This scheme is aligned with whatever the electron domain geometry is. So I think we're in pretty good shape now to be able to do this as our next part of our strategy. So take a second within this one. Which of these in the image do you think is going to require sp hybridized orbitals? So your choices are, and I've tried to designate which atoms. 1, 2, 3, 4, 5, 6, 7, 8, or none of them are going to be sp. So I'm looking at each of the atoms that I've circled in red here. They're all central atoms. And I'm trying to think, is the electron domain there linear? If it is, then I'm going to use sp hybrid orbitals there. And I got to say, as the polling responses come in here, okay, I'm beginning to make sense of it a little bit. When it was first coming in, I was pretty baffled. I think I see what people are saying right now. Take about 10 more seconds. Okay, sharing results on this one. So we had a portion of folks saying none of them are going to be sp hybridized. And then if I look at the two main responses after that, we're seeing a choice for number 9 as a leading choice and a choice for number 5. And I can get that because both 5 and 9, those, or excuse me, 5 and 8, 5 and 8 are drawn similarly. They're both drawn with a oxygen atom and something on the left of it and something on the right. I could see why you might say that would be linear, but it is not. I don't think any of these have a linear electron domain geometry. Both this number 5 and 8, I think the electron domain geometry, I know the electron domain geometry there is a tetrahedral. There are 4 electron domains around that oxygen atom and that one. Lone pair, bond, bond. Those are 4 different electron domains. Lone pair, bond, bond. There are 4 different electron domains there. The electron domain geometry for both of those is a tetrahedral, not linear. So in terms of how many are linear, I don't think any of these are linear. How about the next one, trigonoplanar? Let me send you this one. Which of these would be sp2 hybridized, meaning it's consistent with a trigonoplanar? Select all that apply for that one for me, please. The polling on this one, I'll share it in just a second. It's looking dramatically different. So as that's coming in, I'm thinking trigonal planar. That means I have 3 electron domains. 3 electron domains gives me that triangle shape. 3 electron domains I'm going to describe with sp2 hybrid orbitals. Sharing results within this one. Our consensus is we've got examples like number 1, number 4, number 7. I agree with that. This would be a trigonal planar. I see 3 electron domains, bond, bond, double bond, 3 different directions. Bond, bond, double bond, 3 different directions. Bond, 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 3 different directions. These would be all examples where those atoms have to be sp2 hybridized. The last case, as far as when they have to be tetrahedral, these would be examples where those atoms are sp3 hybridized. We have an example that has 4 bonds. We have an example that includes 2 bonds and 2 lone pairs. We have an example that includes 3 bonds and a lone pair. All of those, though, have a tetrahedral electron domain geometry. All of those atoms would be sp3 hybridized. So if we pause right here as far as what we've been able to accomplish, we've already accomplished a lot. I think that we could look at any of the central atoms, and based on the geometry there, the electron domain geometry, we're going to know the hybridization that goes with it. So right there, I think we're already having a good understanding for what's going on with it. Now, when I say why it requires hybridization, this is the same image that we've seen before. I shared last time about how if you combine an s orbital with a p orbital, it accounts for now a linear electron domain geometry. An S with a P, that's the designation sp2. That's accounting for the trigonal planar. An S with a P and a P, sp3 hybridized, that's explaining the tetrahedral. If you know the electron domain geometry, you know the hybridization for that inner atom. So my plan is we need to know the Lewis structure, and then we need to know what is the electron domain geometry for all of those interior atoms. With that, we know the hybridization. Let me work through a couple examples to show you how this applies. I'm going to perhaps go a little bit quick on these because they're all going to be the same plan. Let's say we're looking at the bonding here in H2O, and we're using valence bond theory. We would start with the Lewis structure. That's what that is. We're thinking about what the VSEPR geometry is, and then we say, okay, I can explain that. I'll use valence bond theory to explain that. That central atom right there, it is a tetrahedral. It is a tetrahedral for the electron domain geometry. Soon as I know it's tetrahedral, I know that that central atom must be sp3 hybridized, because sp3 goes along with a tetrahedral electron domain. Each of the hydrogen atoms, they're on the outside. I'm just going to use the 1s orbital that it has there. I don't have to do anything trickier with that. Those are already set. So what happens for that oxygen atom? It might start out with this electron configuration for its valence electrons, but I'm just going to jump to it quickly and say, I know it's sp3. Let me write together the sp3 for sp3 hybrid orbitals. I put the valence electrons in there. This is now what I would use to explain the bonding. And when I say this would be explaining the bonding, I now have 4 different atomic orbitals. They're pointed in the different directions of the tetrahedral. One of those contains a lone pair. Another one contains a lone pair. This one can form a sigma bond with a hydrogen atom. This one can form a sigma bond with a hydrogen atom. My plan that I did, I started with the Lewis structure. I considered what the geometry was. I then adopted a correct hybridization, and I put the valence electrons in there. That's what I'm using to explain the bonding. Let me show you how it applies for this one. This is one that you had a head start on by looking at within perusal. So the first question was, Let's think about the electron domain geometry for each of these. I see a tetrahedral, a trigonoplanar, and a tetrahedral electron domain geometry. Soon as I know those descriptions, I know what the hybridization is. This one is sp3 because it's a tetrahedral electron domain. The oxygen is sp3 because it's also tetrahedral. And the carbon is trigonoplanar, so it's sp2. If we know the electron domain geometry, we know the hybridization for those atoms. Let me show you now how these end up explaining what's going on with the bonding. So I've shown for each of these what would be the orbital diagram for carbon or oxygen, just as the atom itself. So let's look at this carbon here on the left. We just said that it's sp3 hybridized. So let's draw the 4 sp3 hybrid orbitals. We put 4 valence electrons in them. That can now be used to explain the bonding. One of these will be used for a sigma bond with hydrogen. Another sigma bond with hydrogen. Another sigma bond with hydrogen, and a sigma bond with the carbon. That's how I'm explaining those 4 different bonds. How about this other oxygen? That other oxygen is also sp3 hybridized. I'm grouping together the 4 sp3 hybrid orbitals. One will be for a lone pair, one will be for a lone pair. I can have a sigma bond and another sigma bond. In a way, this oxygen is really similar to what we just saw in water, right? The only difference is one of the sigma bonds in water was to hydrogen, and now that bond is to carbon. Now, both of these, same kind of hybridization because it's the same electron domain geometry. This last one I think is a little bit more interesting, the trigonoplanar one. It's sp2. So this is how I'm going to think about the hybridization and the resulting atomic orbitals for that carbon. I'm going to draw it this way. Notice in all of these cases for the atom before and after hybridization, I end up with the same number of orbitals. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. I'm just changing the grouping of them, what they're designating. I'm not increasing or decreasing the number of orbitals. I still have the same, but I'm just changing what they're representing. I have sp2, that's a total of 3 orbitals, each with a single electron in it, and a leftover p orbital that I have not included in the hybridization scheme. Each of these that are in the sp2, they're explaining the trigonoplanar. Those are going to explain a sigma bond with carbon, a sigma bond with oxygen, and a sigma bond with the other oxygen. The leftover electron that I have in a p orbital, that was not hybridized. Instead of being in that plane, in that triangle plane, it's going to be above and below the plane. It's going to be perpendicular to that. I needed one perpendicular because I needed something off that axis there, off that plane, to make the double bond. That's what that unhybridized p orbital is going to do. In order to make a double bond or a triple bond when we have this hybridization scheme, it's got to be from something that is unhybridized because it's got to be off of that particular axis. Now, how does this idea appear on tests? Let me show you on that. So one way that I've seen this on tests quite often, the easiest way would be to simply take the atom and ask, what kind of hybridization does it have? That's what I mean when I say, can you identify the hybrid orbitals? If you know the electron domain geometry, you can identify the hybrid orbitals. That's usually a pretty high scoring exam question. Next thing we can do is, how do we now describe the resulting bonds using valence bond theory? Let me show you what I mean by that. This particular bond right here, how was that formed? I would say that a sigma bond was formed from the overlap of an sp3 hybrid orbital and an sp2 hybrid orbital. Notice what I'm doing within there. I'm identifying it as a sigma bond, which is a single bond. And then I'm looking to say, well, what atoms did I have on each side of it that were contributing atomic orbitals that would overlap there? The overlap is coming from an sp3 hybridized orbital and an sp2 hybridized orbital. I'm looking at the ones on both sides of that, and I'm using that to say that is what is overlapping to contribute to that sigma bond. Let me show you another example, and we want to try to get to that final goal. Can we describe how the bond is being formed? Let's look at this example. This is one that we looked at last time, but I think we're going to be more knowledgeable now. So first of all, if we're looking at this molecule right there, and we're trying to say, how can valence bond theory explain this? First of all, we now know that those hydrogen atoms on the outside, they're going to be easy. They will contribute only from their 1s atomic orbital. They're on the outside. We don't have to do anything to hybridize them or mess with them whatsoever. The carbon atoms, though, those carbon atoms now, they're on the inside of the molecule. We're going to have to hybridize them. Each of those carbon atoms, I look at it, it is a trigonal planar electron domain geometry. That tells me that each of those carbon atoms is sp2 hybridized. An S and a P and another P atomic orbitals are coming together to form the three that result in the trigonal planar arrangement. That's going to be taking place at each of the carbon atoms. So this is where it's going to end up. sp2 is taking an s orbital and a p orbital and a p orbital, combining those three to make three sp2 hybrid orbitals, and I have a leftover p orbital. Carbon has 4 valence electrons, so I just put them right in there. This is for each of the carbon atoms. This will now be used to explain the bonding that I see in there. Take a second. I'm going to stop talking. Take a second. See if you can think through, how is this being used to explain the bonding that you see in that particular molecule? See if you can think about how the bonding is being explained using valence bond theory. I'll share my answer in just a second. So this is how I would go about using this information to explain the bonding. How would I explain this bond right here? I think I'm forming a sigma bond, which is a single bond between the carbon and the hydrogen. The overlap is coming from an sp2 that was on the carbon and a 1s on the hydrogen. That's what's resulting in all of the sigma bonds that I see between carbon and hydrogen. I think I have a sigma bond that's being formed between the carbon atoms. That's coming from the overlap of an sp2 hybridized orbital and another sp2 hybridized orbital. It's another way of saying, what are these sp2 doing on a given carbon? One is bonding with hydrogen, one is bonding with the other hydrogen, the other is bonding with the carbon in that sigma bond. Recall that when we have a double bond there, first bond we think about as being a sigma bond, and the second is a pi bond. Where's the pi bond coming from? It's between the two carbon atoms, and it's the overlap of those unhybridized p orbitals. They are not in that trigonal planar plane. They're above and below that. They're off of that particular plane. So that's taking place at each of the carbon atoms, and that's what's going to overlap to form then the resulting pi bond. When I say pi bond within that, that's the one that's going to have electron density off of the internuclear axis. Sigma is the one that's going to be along the internuclear axis. And in order to have it off of the internuclear axis and form a pi bond, it must be coming from something that was unhybridized. when I look within this, that's pretty much our end goal for what we want to be able to do with valence bond theory. If I look at a couple end of chapter problems to begin to think about how this shows up, how you can practice it, notice within these first two sets right here, they're saying indicate the hybridization of the central atom. If it's one that's along the outside, we don't need to hybridize that. But the ones that are in here in the central atoms, we do need to hybridize it. I think these are starting out where you first have to draw the appropriate Lewis structure, and then you can apply exactly what we were talking about. Go from the Lewis structure, get the electron domain geometry. From the electron domain geometry, you know now the hybridization. And you could think of, okay, the valence electrons, they're going to be in those hybridized orbitals. In this one down here at the bottom, this is one where it's asking you to simply analyze and determine the hybridization for each of the carbons. If you know, once again, the electron domain geometry, you know it's hybridization. Each of the lines that I have that are single bonds, those are all sigma bonds. When I'm looking at the ones that are double or triple, the second bond there, I have one sigma and then one pi, and this would be a sigma, a pi, and a pi. This question right here, this is really typical of what I would say I'd expect to see on the test. It's really typical because I think it's bringing together a lot of the different ideas. So let's talk through the structure on this one. So first of all, this is showing the general connectivity of the molecule. But it is not showing all of the electrons that you need to have there. After the Lewis structure of the molecule is completed, that means this does not include all of the correct electrons that you need. I know, for example, a carbon atom right here is not going to have a single bond on each side. So the first task that you need to do is you need to add in the electrons in order to complete the environments here. That was something that we practiced when we were first looking at Lewis structures. And then for each of those, we can identify the hybridization because we would have now an appropriate Lewis structure. We would be able to look at the electron domain geometry and think about each of the atoms that we have. Is it sp, sp2, or sp3 hybridized? And then finally, I think we can add to that a little bit. We can describe how each of the bonds was formed. And by saying, how was it formed? What overlapped? Just to give you a hint within there, on this left-hand side, I know that that is an sp3 carbon. It is forming a sigma bond by overlapping with a 1s from the hydrogen. In your analysis here, when you're thinking about something, is it hybridized or unhybridized? We said we do not need to hybridize coming from the ones that are on the exterior, but I'll give you another hint here. When we're looking at things that are double bonds or triple bonds within a molecule like this, those must be coming from unhybridized atomic orbitals. Those must be coming from the leftover p orbitals, because that's what is giving me electron density off of the internuclear axis. Okay. I'll try to put together some questions that are similar to this that you can practice, but I think this is a really high-end sort of finale question for valence bond theory. Okay, now, great, we got about half a class here. Let's get started on aspects of molecular orbital theory. This is one where, no surprise, you're going to have to see molecular orbital theory more than one time. Okay, this is, if you thought valence bond theory was sort of a somewhat new idea, molecular orbital theory, even newer. Okay, you'll be able to do it for sure, but let's try to understand what the concept is. So what is our goal here in 9.7? We want to be able to explain the concept of bonding and anti-bonding molecular orbitals and identify them as sigma or pi. So first thought, we already are familiar a little bit with this notation of sigma and pi. Sigma means along the internuclear axis. Pi means it's off of the internuclear axis. We've talked about things being bonding before, but we got a new idea for us, anti-bonding. That's an idea that's going to be in this molecular orbital theory. I don't know about you, cool idea, anti-bonding. You know, I've heard a lot about bonding. Antibonding, let's see what they mean by that, okay? So let me get at it this way. So first of all, here I show the energy levels that we might have for an atom. We've seen this before. As we start to add electrons, we see a shifting of the energy levels, but we know how to add electrons to something like this, right? We know how to add the electrons and we know what the different symbols represent. We know what 1s represents. We know what 3d represents. So my point is, we can put electrons into an energy level diagram and we know what it represents. So for an example, if you're going to add 8 electrons here, practice that for me. What would be your procedure? Add 8 electrons, and then I'm going to share with you how I do it, because I want us to make sure we're thinking about it the same way. So this would be the way I would be adding the 8 electrons. I'd put 1, 2 in the bottom, 3, 4, 5, 6, 7, and then I would double up. The way I did it is I added them independently, and then I added a second one to complete that. And once I had these degenerate orbitals like the 2p, I added them in independently, and I went back and started to double them up. So I think if you did something similar, you already know how to add electrons to atomic orbitals. So what we're going to do in this next part with molecular orbital theory, we're going to have different pictures that we're going to add electrons to. Here's a depiction from your book about the energy levels when we're looking at molecular orbitals. So what I want to do is spend some time so we understand what does it mean to have this energy level diagram and what are molecular orbitals. So to talk you through this image right here, on both the left and the right-hand side, what they're trying to show there, those are the energy levels for the atoms initially. They didn't show the 1s down below, but you see you have a 2s and then the 2p, just like here, 2s and 2p. So on the far sides, on the left and the right, those are where you would have the electrons in the atoms themselves. Then what it's saying is, in the part in between, these are new orbitals that are being formed. These are orbitals that don't belong to the atoms. These are orbitals that are present in the molecule itself. That's what it means when it says molecular orbitals. We're using atomic orbitals to make molecular orbitals. And that's what's shown in the center here. We have different designations for these. I see the designation sigma. So we already know what sigma means. Sigma means along the internuclear axis. So I think we sort of have a head start on that. So what we're going to do is we're going to be constructing and populating these molecular orbitals. When we do this, we're interested in using the total number of the electrons. When we make these molecular orbitals right here, one atom doesn't own a molecular orbital. We're going to be interested in the molecular orbitals that exist for the entire molecule itself. In fact, after we make these molecular orbitals, we don't really even have atomic orbitals anymore, right? If you take 2 atoms and you stick them together to form this new molecule, in molecular orbital theory, you worry about the molecule. You do not worry about the 2 atoms that you stuck together there. We're interested in these new orbitals called molecular orbitals that form. Now, you might think this could get complex, because if I'm sticking together these different atomic orbitals to make molecular orbitals, that could lead to a pretty complex picture. And you're absolutely right. We are only going to use this approach in this class for some very simple diatomic molecules and ions. Maybe things like F2, maybe things like N2 plus or N2 minus. We're only going to be looking at this with 2 different atoms combining, or if we make an ion of those. So if I think about these as far as what you can do, the skills you have, if you can write the electron configuration, I'm sure you can determine the total number of electrons. This idea of forming molecular orbitals, that's going to be new for us. So you're going to have to work a little bit here to try to learn what do those new molecular orbitals look like. We're going to practice that. When we have that information, what will we use it for? We'll be able to use it to think about things like bond length, bond enthalpy, and we're going to be able to add a new property that we haven't talked about, which are the magnetic properties of the molecule. So if I were to contrast this with valence bond theory, within valence bond theory, we were looking at the atom itself and we were changing its atomic orbitals to make new hybrid orbitals. It might be explained in a trigonal planar, or it might be explained in a tetrahedral. That's what we were just working on. We were taking the atomic orbitals at that atom and we were manipulating them. We were turning them into new hybrid orbitals at times. With valence bond theory, we are not going to make hybrid orbitals. We're going to keep the atomic orbitals as they are. And instead, we're going to bring those together and make new molecular orbitals. So with molecular orbital theory, with MO theory, we don't worry about hybridization at all. Let me talk us through now a few different representations for what does it mean to be making these molecular orbitals. So let's start with our simplest case, H2. So in this representation, what I'm trying to show is you've got a hydrogen atom on the left and a hydrogen atom on the right. They are approaching each other, and those 1s orbitals are coming closer together. That's what I'm trying to show in this picture. How does this now lead to molecular orbitals? So if I think back to my kid that I had in the bathtub, child in the bathtub, an atomic orbital, it's like a standing wave. And what happens when you bring one wave with another wave? Well, they interact with each other. They interact with each other. The manner in which they interact depends on the phase of the wave. So this is, I think we're getting to some really cool ideas, okay? We're taking things you may have heard about waves before, and now we're thinking about what does it mean to have a model for our bonding here. So when I say, what happens when you bring one wave with another and it depends on the phase of a wave, that depends at a given point in time, is it pointed up or down? Okay, is it up or down? These two waves right here that I show on the left-hand side have exactly the same wavelength. They're matched up perfectly. Every time this one is up, the other one is up. Every time it's down, it's down. If you were to take these two waves and add them together, you would have what's called constructive interference. It would increase the intensity of the waves. So waves can be added together and reinforced constructively. Notice this one on the right. In this case, the waves are identical, but the phases are different. When one is up, the other one is down. They're opposite throughout. If you add these together, what happens when one wave interacts with another wave? If the phases are completely opposite, it cancels out. This is a really cool phenomena, okay? How you can have waves constructively interfere to get bigger or destructively interfere to vanish away. This is how like a noise canceling headphones work. A noise canceling headphone, what it does is it doesn't like block it out like it's just making a barrier. What a noise canceling one does, it detects the sound that is coming in and it mixes with that a wave that's opposite. It employs destructive interference to cancel it away. It is taking one sound and combining with another sound, but the phases are opposite and it reduces the intensity. How amazing is that? That's the phenomena that we have going on here, okay? If you bring together a 1s orbital and another 1s orbital, thinking about them as waves, if the phases overlap, they would have constructive interference, and it would give us a picture like this. This is trying to show that you're bringing together two atoms, constructive interference, and you now have electron density between the two nuclei. Electron density between the two nuclei, I call that a bond. When constructive interference occurs, we have an electron density being found between the two nuclei. Along this internuclear axis, that's why we call it a sigma bond. This is a bonding molecular orbital. What if we think about the opposite? We bring the 1s together with another 1s together. What if we have a scenario where the phases are completely opposite? I'm trying to show the phases as having different colors here. When these come together, we're going to have destructive interference. They come together, they interact. In the region where they interact, it's removing electron density. Destructive interference is taking place here. It creates a node there. It creates a region where you do not have electron density. By combining these, if the phases did not match, what you've just done is you've made it so electron density cannot be in the region between the two atoms. Destructive interference occurred. This made it so electron density was not found in the space between the two atoms. You had a node there instead. This is called antibonding. This is an antibonding molecular orbital. When you have electrons in an antibonding molecular orbital, it's as if they're destroying the bond. They are removing electron density from the region in between the two atoms where you need it to have the glue to hold the atoms together. This is the concept for what's taking place with molecular orbital theory. When we bring together this 1s orbital with another 1s orbital, both of these types of phenomena take place. When I bring together a 1s with another 1s, I will form a sigma bonding molecular orbital. I will at the same time form a sigma antibonding. It's given this designation sigma star. This designation sigma 1s is saying you've got a constructive interference. You've got electron density found along the internuclear axis. Sigma 1s star says you are removing electron density from along that internuclear axis. So I know within here, a lot of new ideas for you. Let me show you how another textbook has figures for exactly the same thing. So within this book, on the left side and the right side, they're showing that's where the atomic orbitals start. They're showing how you can bring together one of the 1s orbitals with the other. What you're actually bringing together are their atomic wave functions. And we're interested now in the resulting shape. They're trying to show that both of the phase matches, they were both up. When they came together, we now have electron density being found between both of the two nuclei. That's what it's trying to show with this resulting description right here, the molecular orbital. This is a sigma molecular orbital. Electron density is found along the internuclear axis. Now, I've looked at this figure much longer than you have, okay? Now, I know in this image, right, I'm going to tell you something completely unchemistry related. If you look at this figure right here, sure looks like it is a sphere, and they've made this line in between. Now, if you look at that, that line has to be horizontal, right? Don't you think they drew that line so it's exactly horizontal? So I think that, you know, so as an image, there is a sphere with a horizontal line in it, okay? But the way our brains work, if I look at that, do you see a smiley face there? Do you see that as a horizontal line? Or does it seem like now it might be just bowed just a little bit, so it's a little bit as a smiley face? Am I crazy? Or is there a hint of a smile there? I don't see the face. Anyways, okay, maybe I've looked at this too long, okay? Now, that would be how they're trying to represent the bonding molecular orbital. At the top here, they're trying to represent the opposite. They're saying you can bring together one of the wave functions and the other one, if it's opposite in phase, one's pointed up, one's pointed down. When you add those together, the resulting blue line, notice it goes right through the 0 point right here. It's putting a node right there between the two nuclei. This would be the antibonding molecular orbital. Now, within that set right here, I've shared information in different ways. We're going to continue to work on this, but I think there are 3 skills that I need you to have. One skill is I need you to be able to add electrons to the molecular orbitals and calculate things like the bond order. We're going to practice that in just a second. Second, I need you to be able to recognize what these resulting shapes are and add designations like this. Both of these are sigma because they both are putting electron density along the internuclear axes. This one is anti-bonding, sigma star, because it has a node between the two. So we need to be able to recognize shapes like these. And then finally, we need to know, where do the shapes go on the diagram? Those are the 3 different skills that we need here when we're going to be looking at molecular orbital theory. Populating the diagram, understanding the images, and connecting the images to the diagram. So let's work through a couple of these parts. So this one summarizes what happens if we have constructive interference taking place and we're forming a sigma bond, destructive interference taking place and we're forming a sigma star antibonding. These are the resulting molecular orbitals that form in the center when I bring a 1s orbital and another 1s orbital together. So now let's fill them up. When I'm adding them, notice I'm going to add them to the bonding before I add them to the antibonding. Just like before, we would start from the lower energy levels and move our way up. Same thing here. We're going to begin by populating the bonding, and then we will populate the antibonding. You know how to do that. You did that for atomic orbitals. Now we're just doing the same thing with molecular orbitals. We're going to fill them up the usual way. We're going to have to adhere to the Pauli exclusion principle and Hund's rule, but you already know how to do that. So in this case, I have 2 electrons that I'm going to be adding. I'm going to take those 2 electrons and I'm going to put them in the lowest energy level. That box right there, like any of the other boxes we draw, it can hold 2 electrons, 1 spin up and 1 spin down. I've populated that molecular orbital. After I do that, I don't even have these atomic orbitals anymore. I've taken the 2 electrons that were there and I've populated them into that molecular orbital. We want to be able to now look at how we've populated the molecular orbitals and calculate the bond order. We've already talked about the bond order before, where we talked about a single bond having a bond order of 1, a double bond, a bond order of 2. When we looked at resonance, we had fractional bond orders. Nitrate had a fractional bond order, for example. The way that we calculate it when we're using molecular orbital theory is shown here. We're going to take 1/2 of the number of the bonding electrons minus the antibonding. So in this picture right here, I see 2 electrons in the bonding, no electrons in the antibonding. 2 minus 0, cut that in half, bond order of 1. This is how molecular orbital theory explains what we already know. There is a single bond in the H2 molecule. There is a bond order of 1 in H2. This is how molecular orbital theory explains that. Now, what we're going to do, this was combining 1 hydrogen atom with another hydrogen atom. Our plan is we're just going to keep moving along. Let's see what's next. After hydrogen comes helium. So within helium, I've got a helium atom combined with another helium atom. We're going to populate the corresponding molecular orbitals. I know what the molecular orbitals are. They're exactly the same one that I've seen before. I have a sigma 1 that's going to be bonding and a sigma star that is going to be anti-bonding. Let's take the 4 electrons and put it into those molecular orbitals. I have 2 that I put in the bonding, and then 2 into the anti-bonding. My bond order, when I was looking at it in H2, it gave me a single bond. Look at what the bond order is in helium-2. I've got 2 in the bonding. That would have added electron density between the 2 nuclei. Then I've added 2 to the anti-bonding. Those serve to remove electron density. So after I have 2 in the bonding, 2 in the anti-bonding, 2 minus 2, cut that in half, is 0. This is how molecular orbital theory predicts there will not be a bond in the He2 molecule. Aha, same, that's what we would have said before. We haven't seen any bonding in helium-2 before. This is how molecular orbital theory predicts and explains that. Now, when I say molecular orbital theory predicts and explains this, a lot of times students say, well, which theory is right? You've talked about Lewis theory for bonding, then valence bond theory, now molecular orbital theory. Well, which one's right? They are becoming increasingly more complex. We are going to see the best one is molecular orbital theory. And by best, I mean, which one it explains the most, which one gives us information that the other theories do not, which one, if you are a practicing chemist, would you say is correct? It's molecular orbital theory. We're looking at it for these very simple examples, but this is why insights for this are important when you take organic chemistry. Let's try it within this one. So we've already looked at for hydrogen. We saw we had a single bond in H2. We've looked at it for helium, and we found that there is not a bond in helium-2. How about this next one? What atoms are we combining here? Well, if I look, I've got one atom being described on the left side, one atom being described on the right. Each of those atoms are 1s2, 2s1. So these look like they're lithium atoms. So what we're bringing together, the electron configuration of 1s2, 2s1, 1s2, 2s1, we're bringing together and we're talking about the bonding in Li2. So we've moved past our first row, we're moving to our second row now. So how do we do this? Let me show you what the molecular orbitals look like here. We would have a sigma, sigma star that's being formed by the 1s. We have a sigma and a sigma star being formed by the 2s. In both of these cases, this is what happens when an s orbital combines with another s orbital. You form both a bonding and an anti-bonding arrangement. And these are the energy levels that we then have. Notice how they were populated. There was a total of 1, 2, 3, 4, 5, 6 electrons being put in here. So then when they were being populated in the molecular orbitals, 1, 2, 3, 4, 5, 6. This is what I would use to then describe the bonding in Li2. If I connect this back to our images, when I'm thinking sigma, that would be one with the electron density along the internuclear axis. In a bonding arrangement, the electron density is found in between. Sigma star, it's along the internuclear axis, but there's a node in between. I'm trying to connect the images then back with this energy level diagram. Now, if I'm trying to calculate the bond order here, we could calculate the bond order using all of these electrons. Nothing wrong with that. I would see a total of 1, 2, 3, 4 in the bonding, and a total of 2 in the anti-bonding. Now, nothing wrong with that. That will work. I'll also point out that these ones right here that had coming from the 1s, we could consider those core electrons. In a sense, they're not really contributing to the overall bonding, because notice I've got them in the bonding and the anti-bonding equal number. So in a sense, if you only wanted to look at the bonding and look at the valence electrons, that would be fine too. That will lead you to the same answer. So if I were to try to calculate the bond order in this one, what would be the bond order in Li2? We're going to work through these different ones right here. Calculate, first of all, the bond order in Li2. Remember, our calculation is bonding minus anti-bonding, and then cut that number in half. So for Li2, I see a total of 1, 2, 3, 4 in the bonding. I have 2 in the anti-bonding. 4 minus 2, cut that in half, bond order of 1. If I now move to the next one, Li2 plus, I don't have to worry about, well, where did that electron leave from to make a cation? I just want to remove one of the electrons that I have from my molecular orbitals. I'm going to remove the electron from the one that is highest in energy. So if I'm trying to make Li2 plus, how would I calculate the bond order there? I'm going to remove one of the electrons to make it a cation, and I'm going to remove this one highest in energy. So instead of having 2 electrons there, I'm down to 1. I think this makes a bond order of 1/2. I have a total of 1, 2, 3 electrons that are in bonding. minus 2 that are in anti-bonding, 3 minus 1, cut that in half. Li2 cation has a bond order of 1/2. Let me work on the anion next. So the anion, we would have started with lithium and we add an electron. Where's it going to go? It's going to go to this next spot that's available. That now gives me a total of 4 electrons that would be in bonding, 3 electrons that are in anti-bonding. 4 minus 3, cut that in half. Bond order of 1/2 in the Li2 minus anion. So notice what I'm doing within each of these. I'm just adding up to get the correct number of electrons, whether it was a neutral molecule, a cation, or an anion. I'm looking to see if they're in bonding or anti-bonding, and I'm using that description. What I'd like you to do now, before we move on to the next two, let me send you a polling question. Do you think you're going to be able to determine the bond order in beryllium-2 and the helium-2 minus anion? Both of them or neither? What do you think you can do?
Dr. Clark, am I able to ask a question about what would, okay, so you said for H2, because the bond order was higher than 0, it was possible. So does that mean that any bond order greater than 0 is a possible molecule?
Yep,
like it can exist?
I agree. I agree.
Okay.
So this one, I like your self-reflection here as far as whether you think you can do it or not. I wish I had a more nuanced poll to get at what ideas you think you can do or can't do on this one. Let me talk it through there, okay? So with beryllium-2, I'd be looking at the periodic table. I'd be saying, okay, what is its electron configuration? Let me now put the correct number of electrons in to populate the molecular orbitals for beryllium-2. Beryllium-2 would have a total of 1, 2, 3, 4, 5, 6, 7, 8 electrons. If I look at the periodic table, it's 1s2, 2s2. If I populate all of those bond order of 0, I don't think you have a beryllium-2 molecule. How about the helium-2 minus? For the helium-2 minus, this would be the ones that I populate. Helium has 2 electrons, 1s2. So if I have 2 of those, it's a total of 4 electrons. I add 1 more because it's looking at the anion. That gives me a bond order of 1/2. In fact, this is one with the bond, as was asked just a moment ago. This is thought to have some stability, the helium-2 minus. It has a weak bond between the 2 helium atoms. This is one that folks speculate is found in the sun, where you've got a lot of helium, a lot of hydrogen bouncing around in different ways. It's speculated that this is something that's present in the sun. Part of stellar activity is this particular molecule, the He2 anion. When we looked at these fractional ones right here, when we looked at bond order before, we talked about single bonds, double bonds, and we saw that the bond order, the strength of the bond, told it something about the enthalpy. We saw that the bond enthalpy, the depth of that well, got larger as we went from a single bond to a double bond. And we also saw fractionals before. And when I say we saw fractional bond order before, that's how we made sense of something like nitrate. That's how we made sense of something like carbonate. We had things like a 4/3 bond. Okay, we were not freaked out. Well, maybe you were. I was not. I said, oh, look, it's a 4/3 bond. Its properties are somewhere between a single bond and a double bond. Same thing here, okay? You can have a bond order of 1/2. It would be weaker than a single bond. I think it would be longer than a single bond. It would have a smaller bond enthalpy, but it would still be a bond. It would still be holding those together at least a little bit. That's how I'm beginning to understand how I can interpret this bond order calculation with what's going on with these other properties. Now, on your test, we give you images like this, okay? Images like this, these are ones that we would use to begin to think about what is the ordering of the molecular orbitals. we see that we have 1s combining with 1s to make sigma and sigma star. 2s combining with 2s to make sigma, sigma star. So these general sort of like empty images, those are ones that I see many times on tests to try to give you a little sense for how the different things are being put together. Now, I want to close with this right here. So we have, again, 3 different skills that we're interested in this part. Adding the electrons to molecular orbitals to calculate the bond order, trying to make sense of the images that we have in the symbols that go with them, and then connecting the two, connecting those molecular orbitals that we formed, if they're bonding or anti-bonding, with where they are on the diagram. Right now, we've looked at ones that correspond to a 1s combining with another 1s, and a 2s combining with another 2s. All that we're going to do in the next class is we're going to continue along that row, and we're going to see that after we combine 1s with 1s, 2s with 2s, what's next for us? We're just going to see how the p orbitals combine with other p orbitals. It's a little bit more complex. These are the resulting molecular orbitals that form, but it's exactly the same plan, exactly the same plan. So let's stop right there. I think we're in a really good space. What we'll do next time is we'll revisit a little bit of what we first introduced here for molecular orbitals, and we'll extend it to see what's going down when we're talking about p orbitals combined with other p orbitals. And I think we're in really good shape to wrap that up next class. As always, I'll hang around if you got questions.
Hey, Dr. Clark, you mentioned like a well when you were talking about the enthalpy.
Yep.
I don't remember exactly. Could you just explain like exactly?
Yeah. I didn't have one of these images, but if you recall the ones where we, it was our potential energy well, where we showed what happens when the atoms are far apart, and as they come together, we see that it goes down to be lower in potential energy. And then you could squeeze them too close together, and that's where the potential energy then goes up. It becomes positive, it goes above 0. So that particular diagram, what I'm calling a well, that's one that we were looking at when we were thinking about how to interpret the enthalpy, for example, the bond enthalpy.
Okay. And then bond enthalpy is like, that's going to be inverse to potential energy?
Well, the bond enthalpy, it only has a value. It doesn't have a sign on it. If I'm thinking about how a bond forms and that's exothermic, I would view that as the energy that's released when the bond forms. Or I could think about it just the flip of it and say, oh, if you already have a bond, that would be the energy it takes now to break the bond.
Okay.
Can you explain how we add electrons to molecular orbitals again?
Yeah, absolutely. So I wanted to start a little bit with saying, I think you already know how to do it, because if you hang with me, were you okay adding electrons to something like this?
Yeah.
Okay, and so we're going to be doing exactly the same thing. We're going to be doing exactly the same thing, but now we're going to be adding those electrons to this region right here in between. We'll be starting at the bottom, and each of the boxes or each of the different lines right here holds 2 electrons just like before. So if we're looking then to add it to something like, let's get it to these 2 examples right here. So if I'm looking at this example with a hydrogen atom with another hydrogen atom, I've got a total of 2 electrons that I'm going to be adding. I'm going to add both of those to this one that's lowest in energy. If I have a total of 4 electrons, I would add 1, 2, 3, 4. I'm adding them in a set of 2 and then another set of 2. That would lead to a bond order of 0. When I'm looking then with something like Li2, I'd add them like this. I have a total of 6 electrons I'm adding. 1, 2, 3, 4. Then I move up to the next spot. 5, 6. That would be then how I have a combination of bonding and anti-bonding here. Help me out within this one right here. What's your question on that?
I feel like I understand that. I was confused about like the sigma bond area, but that makes sense to me. Thank you.
Yeah, well, let me ask you this. Are you able to get when the ones where we're talking about ions?
Yeah, that made sense to me. Yeah.
Oh, good, because a lot of, I don't want to make you confused, but a lot of times students, that's the one part that they get confused with. They're like, okay, which of the atoms gained or lost the electron? And it's sort of like, that's not the point. We're just looking at the total number that is within that set right here. It sounds like within your question is a little bit more, comes back to the designation that goes with it.
Yeah, I think so. Thank you. I also have another question
Mhm.
really quick. So I was looking at a chart that had the like bond angles, and I was just wondering why we don't hybridize um like the trigonal bipyramidal.
Ah, yeah, good question. So within our set right here, valence bond theory, it works really well when we're going up to like a tetrahedral environment. So up to like sp3, and that works great. When I say it's used in organic chemistry, that gets us to carbon, nitrogen, it works great. So that's a really powerful approach. If you go beyond that, well, you've got to go beyond having an S, a P, a P, a P. You've got to start to add in other features too. And a lot of times that you'll see, like in textbooks, they'll say, well, now let's just add in d orbitals. Let's add in other ones. Now, your textbook right there, I know the author on that, that's no longer really thought of as being correct. They don't really think you can make hybrid orbitals out of that. And I know a lot of students like within this, if they've seen it in high school, they say, oh, well, we'll just call this a DSP3 or a D2 in order to go beyond that. But these authors say, no, that's not really what's taking place. So I think that's a limitation of valence bond theory. I think you're trying to make it explain something that it really can't do a very good job with. So in our case, we're only going to take it to a tetrahedral arrangement. I'm confident it works well there, and you're not going to be asked to go beyond that.
Okay, thank you.
Yep.
So I had a question. So this format shows, is it like to the sides? It's showing like the what we're used to, like the electron order. I don't know, what we did before. And then the middle shows how like it actually is with the orbitals and stuff.
Yeah, I like it. So on the left-hand side and the right-hand side, those would be when we are thinking about what were the electrons for the atoms themselves. Lithium would be 1s2, 2s1. So if I were to cover up everything else and I just looked at the left-hand side, I would say, oh, that's describing a lithium atom. And if I look just on the right-hand side, I covered everything else, I'd say, oh, that's describing a lithium atom. And now the orange part in between is saying, oh, but what happens if we bring one lithium atom together with another lithium atom? What are the new molecular orbitals that we form? So after I bring that together and I have this part in between, you're absolutely right. The ones on the left and the right, those are what we already knew when we were thinking about the atoms. Now we are just using those to say, tell me about the molecular orbitals, the new ones that are formed, and let's put the electrons in there instead.
I guess I just got confused because it was never really mentioned that they're like kind of separate things. I thought like looking at the lithium, there's like 12 electrons. That doesn't look right.
I'm with you. And that's what I tried. Like I had one image in here, right here, because you're not alone. This is where I tried to show, look, if you start with them on the outside, after you add them to the middle, forget about the ones on the outside. Because what you're saying is exactly what people get hung up on, because they're saying, look, why do I now have 4 electrons here? We got to forget about the ones on the outside once we begin to populate on the inside here.
I guess I must have missed that.
No, you didn't miss it. You absolutely said what everyone gets confused about. You've absolutely, so I'm glad you brought it up. That's exactly the point. And because I think these images are not that clearly representing what's actually going on. These are what we always see, but I completely see your point on it.
All right, thanks.
Yep.
When we're determining how to hybridize orbitals, is the way that we know to leave, for example, like one normal p orbital, is that we've already, like for example, a trigonal planar, we've already have 3 hybridized orbitals, so any more will just be normal.
Yep, that's correct. So once you know the hybridization and you put together that grouping, There will be cases indeed where you have a leftover unhybridized p orbital. If you do sp, for example, you would have 2 of them left over. And so those remaining ones, those can then participate if you're making double or triple bonds.
Okay. And then is one orbital always going to only overlap with one other orbital?
Correct. Yeah, in valence bond, that's all a given orbital can do.
Okay. And then I have one more question. I don't know. It was in the perusal. You were showing how to hybridize boron,
Mhm.
and then it had 3 sp2 orbitals. And you said there was 1 p orbital left over, but
Yep.
you didn't put any electrons in it. Is that just because
Yeah, so
there's
in that
usually
case right there, so once again, that atom, it started out with, and we had an S and then 3 p orbitals.
Mhm.
We've grouped together an S and a P and a P. Those will now describe the sp2 trigonal planar environment. It still has a p orbital there. Now, it just doesn't have any electrons in it because we only had 3 valence electrons, so we haven't put any electrons into that remaining one. In some ways, boron's sort of unusual that way, because usually if we have a leftover one there, it forms a double bond or it contributes to a double or a triple bond. But with boron, we just don't have enough electrons anymore. So with boron, after we've made our sigma bonds in our sp2, we have a leftover p orbital. It just doesn't have an electron in it.
Okay, so yeah, so it just you always want to conserve the number of orbitals when you're moving.
Yeah, you don't change the number of orbitals. You don't change the number of valence electrons.
Okay.